All right, welcome back. This is one of my favorite lectures to give live because this really synthesizes a lot of what we learned up until this point about linearizing nonlinear dynamical systems, computing the solutions of linear differential equations, and plotting their phase portraits and looking at their eigenvalues and eigenvectors. So I'm going to jump in, and we are basically going to be linearizing nonlinear ODEs and then plotting their phase portraits. And I'm going to start with a physical construct, which is called a particle in a potential well. So the idea is that we're going to consider a potential function, literally like the potential energy, a potential V of x, and imagine dropping a bead or a marble in that potential well. And imagine dropping a particle or a bead, which I'm going to call a bead, and I'll tell you why in a minute, a bead x that can roll down the surface. So we have a potential surface, so this is the x direction, this is V of x. It's literally like the potential energy of being at this height or this height or this height. So you can kind of imagine, maybe gravity's pulling you down, and you have different potential energies at different levels in this potential. And we are dropping a particle or a bead. So I think of this sometimes as a wire, and I've got a little bead that can slip on that wire with no friction, and it can move around on that potential surface. So our bead, and it has position x, so position x. This bead can roll or slide down this potential surface. Okay, words are not as important as the picture. The idea is that I have this potential surface, and I'm putting some particle or some bead on this, and it can kind of roll around or slide around on this potential and do its thing. So if I start with a little bit of energy or potential energy here, and I drop my bead, we assume it's going to oscillate. That's what a marble would do if there is no friction. If I have, if I'm in this well, I will do the same thing. And if I have a little bit more energy, this is why I call it a bead, because I don't want it to fly off. I want it to be constrained to being on this kind of wire surface. It's also going to oscillate around. Okay, and we're going to derive this equations of motion from F equals ma. It's going to be a nonlinear differential equation, and we're going to linearize at different points. So the force is F equals ma. Okay, obviously it's F equals ma. And the force from this potential is always going to be the negative gradient of that potential. This is just, from kind of basic physics. The force is going to be proportional to minus the gradient of the potential, so minus partial V partial x. And this basically says that if this gradient is 0, there's no force moving it, so it stays put. This is a fixed point. When it's flat, there's 3 fixed points here. And when the gradient's not 0, then the force is proportional to kind of how steep this potential is. So the steeper this thing is, partial V partial x, the more force kind of accelerating this thing down. Okay, so the force is proportional to the gradient minus gradient of the potential. And again, if I have a positive grad V, then that's going to be pulling me in the negative direction. And if I have a negative grad V, that's going to be pushing me in the positive direction. That's why I have this minus sign here. And so Newton's second law basically says, Newton's second law, we're very familiar with this now. Newton's second law says that x double dot equals minus partial V partial x. I'm assuming that this bead has mass 1. I don't want to deal with a mass 2 or 5 or m. This is for a mass 1 bead. These are the equations of motion. Okay, so this is really, really easy to deal with. Now, alternatively, I could have derived this not from Newton's law, but from the Euler-Lagrange equations. So maybe I'll just show you. This is kind of a little foray into how you get these nonlinear equations from physics. Yeah, maybe I'll, so this potential function, because v, in this case, this potential function would be like a fourth order polynomial, right? This thing looks like a fourth order polynomial to me. And so grad v is going to be a third order polynomial. And so x double dot is going to be a third order polynomial, and x, that's clearly nonlinear. Okay, so this is how we get nonlinear differential equations, would be like a particle in this potential well. So alternatively, we could use the Lagrangian, could derive from the Lagrangian, Lagrange, which I think is a little bit more general than using Newton's second law. And so what we would do is we would define a kinetic energy and a potential energy. So kinetic energy of our particle is going to be 1/2 x dot squared. So T equals 1/2 x dot squared. Okay, this is just the kinetic energy of this particle. We would define the potential energy of the particle. So the potential energy we've already defined as, v of x. Okay, and the Lagrangian, maybe I'll write that in blue. So the Lagrangian, this is from Lagrange, the great Lagrange, is this function L of both x and x dot, which is equal to my kinetic energy minus my potential energy. So it's this T of x dot minus my V of x, my kinetic minus my potential. That's how this is defined. And we know that this is equal to 1/2 x dot squared minus V of x. That's my Lagrangian. And so the Euler-Lagrange equations are a set of second-order differential equations that are one of the most important sets of equations in all of physics. So the Euler-Lagrange equations, and these come from the principle of least action, which is probably the most universal principle in all of physics. The Euler-Lagrange equations essentially say that the time derivative of the partial derivative of L with respect to x dot minus the partial derivative of L with respect to x equals 0. And again, this is a differential equation. It is a second order differential equation. We'll find that we're going to get, x double dots from this term here. It's a second order ODE that encapsulates the principle of least action. And the principle of least action is probably the most universal law in all of physics. So physicists talk about a grand unifying theory. I'd say they already have one in the principle of least action. It applies to special relativity, general relativity, classical mechanics, quantum mechanics, optics. When light shines through two different media, it takes the path of least, the principle of least action applies. It takes the path of least resistance. So this is super duper useful, the Euler-Lagrange equations, the principle of least action. And you can apply it to this very simple bead on a rotating hoop, and literally partial L partial x dot. This is the only term that has an x dot. So, partial L partial x dot is just using the power rule. I get 2 times 1/2 is 1 times x dot. This just equals x dot, which implies that ddt of partial L partial x dot is x double dot. And similarly, partial L partial x is just minus partial v partial x. Good. And so if I combine these, I basically have, x double dot minus a minus partial v partial x is plus partial v partial x equals 0, which of course implies that x double dot equals minus partial v partial x. Now, of course, that's already what we had from Newton's second law, but the Euler-Lagrange equations are way, way more general. So you can use this basic idea to write down the equations of motion for almost any system, not just mechanical systems, quantum mechanical systems, relativistic systems. If I had, my pendulum here, and I wrote this down in terms of its angle theta and its angular velocity theta dot, I could do the same thing. I'd write down the kinetic energy is, this thing has a length L and a mass m. So the kinetic energy T would be 1/2 m L squared theta dot squared. Okay, that's the kinetic energy of that system. I could write down the potential energy. It's probably something like V equals, mg cos theta. Maybe there's a minus sign here, I forget. But I could write down the potential and the kinetic energy for this system, plug them into the Euler-Lagrange equation, and I will get the equations of motion. Theta double dot equals minus sine theta, right? You can derive the equations of motion for a double pendulum, for almost any mechanical system and almost any physical system at all using these Euler-Lagrange equations. And the neat thing is that this always gives us, essentially a second order system of ODEs, because Newton's second law, this is another way of stating Newton's second law. They're kind of equivalent. This is just maybe a more powerful way of saying it. You're always going to get this this kind of second derivative because of this term here. So this always gives you second order ordinary differential equations. And in general, they're going to be nonlinear, like this sine theta is a nonlinear term here, because this potential function v, this grad v term here, is generally going to be a nonlinear potential. It's going to have some weird funky shape. And so you're going to get these nonlinear terms in your second order ODE. Okay, so I think what I'm going to do in the next lecture is I'm going to take an example of some potential, probably, v equals x squared over 2 minus x cubed over 3, something that looks like that. And we're going to derive the differential equation x double dot equals, minus the grad of this is minus x plus x squared. We're going to find its fixed points. We're going to linearize about those fixed points, and we're going to draw the phase portrait. This is going to be a beautiful culmination of everything we've done. We can now analyze nonlinear differential equations that come from a broad class of interesting physical systems, and we're going to specifically linearize about the fixed points here and here. We're going to find the eigenvalues and eigenvectors of those linearizations to classify their stability and what the local dynamics look like. And then we're going to be able to draw these really rich phase portraits showing what the global structure of trajectories of the system are. So really, really cool stuff. That's all coming up next. So looking forward to showing you that. Thank you.